afternoon. So right now Dominik Csiba is going to speak about the role of optimization in machine learning, but before that I would like to thank Slido for helping us use their awesome tool for discussion. Also thanks CAI for sponsoring this event. And I'm happy that you all came here, and I pass the mic to Dominik.
Can you please start the presentation? Okay, so hello everybody. I had been asked to do this presentation in English. I hope that it's not going to be as bad. And first of all, thanks to all of you that you managed to come here, you know, in this rainy, snowy afternoon, because if this would be a different talk, I would probably not come, so, you know. So I would like to talk about the role of optimization in machine learning, and it's going to be a talk from my perspective as a PhD student doing optimization in machine learning. So maybe some of the opinions are going to be very subjective, but please, you know, forgive me for that. And if you have any questions at any time, just raise your hand and I will answer them straight away, okay? Good. So the first part is basically about motivation. So why do I actually want to talk about optimization in machine learning? And the reason is simple. And most of the machine learning models can be written down as some sort of optimization problems at the end. So if we take just for example linear regression, as it is used in most cases, or linear classification, or logistic regression it's often called, they can be written down as a very simple optimization model. Beware now, there's going to be some math involved, okay? So don't freak out, don't run away, it's going to be fine, okay? If you won't follow, it's fine, it's not important, actually. So this problem can be actually rewritten as something like this, which looks slightly scary for somebody who did not do math before, but it's actually not that complicated, and I will walk you through this. This problem is known as the lasso problem. It's a very famous problem in statistics. And then there is the second problem, which was the plot on the right side, which is the logistic regression. And you see that there are some similarities to the problems, and let's just look at them as, you know, somehow structural. So both of these problems contain this term, which is some sort of loss function, which is basically telling you that how well did you fit the data point to the observed value. So if we go back here, it just means that how far is this point from here. That's it. Okay? That's the loss function. Here it is quite straightforward. Here it's slightly more complicated, but one can reason for it, that why it looks like this. It's some math, you know, it's not that important. So the second part is the regularizer, which kind of prevents something with what's called overfitting. You've probably heard about it. Again, it's a mathy thing, and the optimization algorithms in practice do it by themselves, so you do not really have to take care of it. And then we have the features from the examples. Those are basically just some numbers, you know, like the weight, height of some sort of person, or you know, the salary and so on. And then there is some label, meaning that, you know, in which city do they live in, or something like that. So this is somehow the basic structure of an optimization problem. So what it means is that we are trying to find this vector W, which is minimizing this term. So it's a vector W for which this term is the smallest from all the W's considered. And this is basically the basic setup of the optimization. And yeah, you probably all seen this example, you know, so many times that it's not interesting and I should not go into that much detail. So, you know, probably you are going to appreciate it when the more complicated examples come. So the first example that I have is the so-called Dimensionality Reduction, or the PCA, where the idea is to do some sort of unsupervised learning, which means that we have this cloud of data points, and apparently the more important direction in the data points is this one. It's way more important than this one, and in some sense we can actually discard this direction and just look at them as one-dimensional data. And this is actually quite important in many applications. but not in 2 dimensions. But if you have like 1,000-dimensional data and you want to kind of project it into 2 dimensions and see what they actually represent, if you do the best possible projection, if you draw the best possible line through this cloud, what it is going to represent, it's very useful. For example, there was this paper published in Nature, I think, where they called about some sort of DNA things, you know, some sort of genome, whatever stuff. Those are some very high dimensional features. They projected it into 2D. They labeled each of the data points by the country where the person came from, and voila, that's the map of Europe, right? And it's great, and everybody liked it, and it was published in Nature, and that's what you need to do to get a paper published in Nature, right? Just something cool, and it does not have to be accurate or whatever. Because, you know, for example, Slovakia has a cluster down here in Italy, so I actually do not understand. So, yeah, and let's rewrite this problem as optimization, and this looks probably slightly more complicated, not much. So again, we have some sort of loss function. This just means that how far is the data point from the projected data point. We have some constraint, which means that the vectors that we are trying to find are going to be orthogonal to each other and of 1 length. And then again, we have the features, and here we have the principal components, which means that the principal directions. That's it, nothing more. Okay, let's go further. So we have some sort of matrix completion task, which basically means that, let's say that one of the axes are the users, the second axis are the videos on YouTube, and every person either liked, disliked, or did not see the video, right? And this just means that, okay, we have this user, he liked this one about cats, this one about dogs, he disliked this one about cars, and about, I don't know, sci-fi movies, right? So let's just try to predict that each of those users, whether he will like or not the rest of the movies. And how it's done, it's basically a very simple approach. This one that I'm going to present, which is just try to fill in the matrix such that the matrix is going to have the smallest possible rank. Rank is just some sort of mathematical property. Again, it's not important. Basically, it just means that, you know, all of these vectors are just either the same as this one or the minus of this one. It just means that, you know, everybody acts the same, basically. So that's what we are trying to achieve. And if we write it down as an optimization problem, it's just minimizing the rank. The rank of some matrix X should be as small as possible, while it holds that the values which we have at the beginning are the same in the new matrix as they were in the old matrix. That's it. Nothing fancy, nothing more complicated, it's just it. Okay, everybody's following so far? Any questions? Okay, so I have one more example, which is probably slightly more non-standard. It's one thing that I was working on while I was interning at Amazon, and they were interested in this real-time bidding in online advertising, which sounds super complicated, but it's actually not. So suppose that you have some sort of web page, and there is a banner where you can put an ad on the web page. So what is actually happening behind is that there is an auction being created for all the advertisers, and there are some sort of competitors who want to have their ad displayed on that web page for that given user who actually opened the web page. And the first competitor says that I want to have this ad there on some computers for 10 cents. I want to have this football there for 5 cents, and I want to have, I don't know, nuclear weapons, probably Worms Armageddon, something like that, for 1 cent. And okay, so the highest bid wins, and that ad is going to appear for the user on the web page. And this is actually happening behind the scenes when you browse the web, right? So the question is that how to do this from the point of view of a competitor in these auctions. So as a competitor, for example, Amazon has a whole swarm of ads that he wants to show. That swarm of ads is basically paid for from some company. So, for example, Adidas says that spend please $100 on this football, $100 on these trainers, then you have, you know, some other company, Intel or whatever, and you are just displaying ads this way. So if you want to rewrite it as some sort of optimization problem, this starts to get complicated, but it's still, you know, parsable in some sense. So first term is this utility function. It just means that how good it is to show this ad to the given user. But there is one complication, that usually you do not know that what kind of user is going to come in like half an hour or in 1 day. So these utility functions, they arrive sequentially, which means that we do not know them up front like all of the previous ones. And then we have the second term, which in this sense is some sort of penalty. What it means is that if Adidas told us to spend $100 on the football and we are going to spend 1 million, probably they are going to be mad, right? On the other hand, if we spend 0, they are also going to be mad, right? So this penalty term is just trying to make sure that in long term we are going to spend exactly 100. And this is some sort of online optimization with a long-term constraint, which is not as trivial as it looks. And I had quite some fun with it. So if you want to have some fun, I recommend you to look at it. Or, yeah, probably not. These are just some sort of feasible allocations. It just means that, you know, you do not want to show some ads to some users and so on. Probably men are not interested in lipsticks and so on. So, you know, sorry for me being sexist, but I think that this is a general thing. The XTs are just the allocations, the ATs just encode the spend, and the BT just encode the budgets. It's not important that you understand this like exactly, it's just the idea that this is also just an optimization problem. Okay, any questions so far? I think that this is closing up the motivational chapter. Good, or not so good, I don't know. Okay, I have one more slide. So what to learn from this is that most of the learning which appears in machine learning actually boils down to some sort of optimization problem. And because of this, many mathematicians are actually attracted to machine learning because, you know, there's some mathematics in a different way that it's usual. You know, it's not just finance, it's not just statistics. Okay, machine learning is very close to statistics, very similar to statistics, but, you know, optimization is at least slightly different. So this is the reason why it's the main topic of my PhD, I suppose. And also, the optimization community has its own ecosystem inside the whole machine learning, you know, community again. Bunch of people, you know, or something like that. What it means is that there are a bunch of mathematicians who do just optimization and nobody understands them from the rest of the machine learning community, right? This is either good or bad, you know, depends on which side you are. But yeah, it's actually quite nice to look at them from, you know, both sides now. What's important about machine learning is that for most of the practitioners, it's actually not important at all, right? Why? Because it just works. If you just call a function, I don't know, .fit at any of the programming language doing machine learning, it's just going to learn those parameters, right? It's just going to figure out that optimization problem for you. So actually, why it is important? In some sense, it isn't, right? And we could stop this talk right now. That's it, right? It's not important. But there is another perspective, and that is that if something goes wrong, actually it's important to understand the optimization part of the whole machine learning process. So yes, there is a phone ringing in my pocket. Let's just mute this. Okay. So other than that the black box gets faster and faster each year, that's probably the only thing that the practitioners notice, that, oh, it got faster. They do not know how, right? It just got faster. Okay, good, good. 10 times faster, good. Something happened, it's 10 times faster. It does the same, but 10 times faster. Good, right? Okay, so we save some money. Other than that, only thing that matters for practitioners is that if the learning fails somehow, like the learned vector, the learned parameters and so on, do not do what I expect them to do, then it is trouble, and then it's time to call somebody who understands what the fit is doing, right? And what I would like to do is to just describe you some scenarios which are known to cause some issues for the fit function, just to get a flavor of what could happen. And just in a very specific regime, which is supervised learning, there is a whole lot of different stuff that can happen in the rest of the machine learning. Yeah. So, everybody's following? I see some nodding from the back, so I suppose that's okay. Okay, still I would like to have just at least 2 questions right now. Yes?
Why do you think that supervised learning is different from unsupervised for this optimization problem?
So from the optimization perspective, I think that the supervised learning is different from unsupervised because it's easier. If you look at the problem, then the unsupervised learning is basically the PCA, for example, right? And that problem is non-convex. If that word rings a bell, I hope it does, it just means that it's very difficult, right? While the supervised problems are often nicely structured and they are easier to optimize. So from the optimization point of view, they are completely different worlds, and some of them are more difficult and, you know, they're just different in some sense. I don't know whether that's sufficient. Yeah. Okay, one more question? One more question?
What about reinforcement learning?
What about reinforcement learning? That's a good question. I'm glad you asked. I'm just reading a book on reinforcement learning, and I realized that how much optimization there is. So, yeah, in reinforcement learning, I don't know whether you are familiar with reinforcement learning. It's some sort of learning where, you know, think about learning the game of Go to play, you know, to beat the world champion. So that was reinforcement learning, right? So in some sense, we are just trying to learn some strategy, not just to make a simple decision, like, is that a brain tumor or not? But to figure out that what to do in a given situation, like a complex decision-making procedure. So the AlphaGo that was trained using reinforcement learning, and it has some similarities, but also there are many differences. For example, you can actually choose how your agent is going to act in the environment and what kind of training examples you are going to get. If you want to figure out what to do in this specific position, you can just put it on the board and play it out, figure out what is going to happen. But usually, this is something you cannot do in supervised learning. You just cannot ask, you know, tell me what is this picture? Noise, okay. But, you know, what is this picture? A cat, you know, dog. But you cannot actively ask when you are learning. The algorithm itself cannot ask for specific pictures. In reinforcement learning, it can. So, but on the other hand, in reinforcement learning, it also needs to do some actions, and the actions are rewarded during the time that it does the decisions, right? So, it's more complex also. It's more complex from the point of view that your decisions have to be good even through training time, if this makes sense, which makes situation a little bit more complicated. So again, it's a different ecosystem and it's very interesting. So I definitely recommend you to look at it. Okay, so let's move on. Those were the 2 questions that I asked for. Okay, so let me just quickly go through supervised learning, what that actually is, right? For those of you who are not sure or, you know, have not heard about it. So, supervised learning, you have some world, the world produces examples, pictures of cats, right? And labels that it is indeed a cat, right? That's it. And what you want to do is to train some sort of function which is going to, from each image to each label, give you that what it is, right? What it means is that this is a cat, right? This is not a brat, because it's a dog, right? So this is a dog, right? That's it. That's just it. So we are just trying to find this great function which can do this, right? And you can see that it's difficult, right? Even a human eye could actually miss this. Yeah, so how to do this? There is this very basic method called empirical risk minimization, which is that you just look at a bunch of pictures and you just minimize some sort of error. That, you know, this just means that what did I predict about the picture and what is the true value of the picture? You know, I predicted dog, it's cat, that's quite bad, right? I predicted very bad. So that's some sort of error of 1, let's say, and I'm just trying to minimize, you know, that how many pictures have I misclassified. That's it. And usually I have some hypothesis class, which means that I'm not looking at everything, but just neural networks or, you know, linear models or whatever. It's not important for this talk. But the important part is the loss function. There is some loss function, and it's some function. That's it. We've already seen a couple of them in the first slide. Those linear models, those were loss functions. And we just hope, in some sense, that this minimizer of this thing is going to be close to the true one, right? If we look at a bunch of cats, we hope that we are going to recognize what is a cat in the future. That's it. And usually how the optimization looks like is just we are trying to minimize some sort of function, which is an average over smaller functions. You can think about it that average of these losses is just rewritten in a more compact form. It just depends on W and that's it. Yeah, there's going to be some math involved now that I think about it. Never mind, you are going to make it. So the optimization task is to solve this in some sort of general way. And how does the optimization work? I always think about it this way. So the task is to find the bottom of the valley, right? So think about this map and try to find the bottom, right? That's it. But to make things more complicated and more easier at the same time, you are in a dense fog, so you do not see a thing, right? You're just standing in the valley somehow, you do not know where you are, you know, or what is around. You just know that you are standing somewhere, right? You can use a teleport, however, so that's quite good. And you can also ask for some information. And the information you can ask for is the altitude of some location. So I know that this is 100 meters, so there is going to be, you know, hopefully similar. I can ask for the slope at any location. And usually I can also ask for some sort of curvature at a given location. And probably some of you recognize this as, you know, the function value, the first derivative, and the second derivative. For the geeks of you, basically. And the most popular is to look at the slope, because actually the slope has a lot of information in it. And if you just use the slope and figure out that, okay, I'm standing like this, so probably down is that way, right? Then you get this algorithm, which just means that, okay, do a small step that way. That's it. And hopefully you are going to hit the bottom. It's just mathematically rewritten. So, yes, this is the gradient for those of you who actually know gradients. Good job. So we do a step down the hill, but it's actually quite more complicated because it's not so easy to do steps down the hill. Because think about this function. If the step is too small, you are just going to take a lot of steps to reach the bottom. If it's too big, you are just going to take a lot of steps jumping over the bottom to actually reach the bottom, right? If the step is, you know, reasonable, it's going to be fine. So that's just a quick recap of supervised learning. Hopefully, most of it was actually known to you. And now what I want to talk about is the first complication, which is quite disturbing in these days, and that's big data. What does big data mean? So think about doing some sort of classification on, I don't know, all the users and videos on YouTube, right? That's like billions times trillions, I think, last time that I checked. So that's quite huge, right? If you want to do anything at that sort of scale, it's going to be complicated. And it's going to require, you know, some different kind of attention and some different kind of methods than they are usually used. So when I think about big data, and this is going to be just these 2 slides or so, are going to be slightly more mathy. So if you just want, just go, you know, go for a beer or something like that. The other ones Sure, look at it, it's going to be interesting. So, large-scale data, what it means that if you are going to do the gradient descent algorithm, this gradient, because we are in many dimensions, this is actually a multi-dimensional thing. And this notation may freak you out, but it just means that the first entry, the second, and so on, you know, dth entry of the gradient. To actually compute the gradient, we have to compute every one of those entries. We cannot do them like, you know, in one step. We actually need to compute every one of them. So, one after the other. Okay? And also, as I told you, that the function we are optimizing is actually a sum over something, or a mean over something. It just means that to compute the gradient, using the sum rule, we actually have to compute the gradient of each of one of those functions, of those fi's. Which means that we need to compute number of examples times the small gradient. And now, just a simple math, this is d, this is n, right? So to actually compute the whole gradient, we need to do n times d computations of those small partial derivatives. That's it. And that's a lot for one step. Think about billion times trillion, right? I do not know how big that number is. It's just, you know, I cannot even perceive it. So, yeah, that's a lot. So because of this, there were two strategies developed how to overcome this. The first one basically says that, okay, let's just ignore most of them and take just one, and just move in one direction along one dimension. And the second one is, okay, just discard everything except one, and just, you know, hope that the slope information of one of those functions is going to be similar to this, you know, slope information of all the functions combined, which is kind of weird assumption, but it seems to work. Okay, and this was too mathy, so let me illustrate those ideas on some pictures, okay? So, gradient descent, what I said is actually the best we can do just using first order information in some sense. Let's just not talk about acceleration, those of you who are raising your hands already. So, it looks like this, and the step size is just constant, and as I said, the iteration cost is just dependent on the number of examples and on dimensions as well. So how I look at it is a wrong step in a smart direction. What it means is that we spend a lot of computational resources to find a good direction, but we can take only a small step because we are not sure how does the function change along that direction. Okay, so how does it look like? We are starting here, and here is the bottom. Think about this as contours on the map, right? So this is the bottom. And we just, you know, take the gradient, we just look at down the slope and we just take a step. Step, 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 and we hit the bottom. That's it. It looks as the gradient is always going in a straight line, but think about starting here, then we would go like this direction, then this direction, then this direction, then this direction, right? This is just that I started from a weird spot. Okay? I suppose that most of you already seen a picture like this, because gradient descent is quite famous. Okay, and now, yeah, it's actually solved. Good. So the second one that I talked about is the randomized coordinate descent, and what it means is that we are updating things just along one direction at a time. So it looks like this. It's not important. It's not important, but it's independent of dimension. That is important because we are not computing every dimension but just one. And how I look at it is that it's a smart step in the wrong direction. Why? Because the direction is completely wrong, right? We are just going down one coordinate, right? That's it. But on the other hand, because that's just optimization through one dimension, we can usually optimize it very well because it's just one-dimensional optimization. We can spend some time to actually do a very, very reasonable step. So, back on this picture, we throw a coin, we decide on a direction, and we just go in that direction. Throw a coin, oh, the other way around, good. So now we are just going to the minimum along this direction. This is the minimal contour. And again, and again, and again, and again, and again, and it's solved. That's it. So this looks like a very basic idea, and a very trivial one, but think about this in million dimensions, right? In million dimensions, you would throw a coin, with million sides. Probably a dice, or something like, more complicated. Just generate a random number from 1 to million. That's fine. And then just decide on the dimension depending on this, and just do a step down the direction, the best you can do. Then choose another dimension and just go. Go, and you will converge. You will eventually converge, and it's going to be faster than gradient descent, usually. Or you can actually prove that it's going to be faster. Okay? Any questions?
You said you can prove it.
I can prove it, I'm not going to do this. We can talk about it offline, or I can just direct you to some papers. Good. By the way, just typing randomized gradient descent into Google will do it, right? But I really want to talk to you, okay? That's fine. Okay, and now we have this stochastic gradient descent, which I described before, that you just take one of those functions, you just discard everything else. And the step size has to be decaying, which means that it, slowly goes to 0. I will comment on this later. And it's independent of the number of examples. And this is actually an algorithm which is very widely used in machine learning. It's probably stochastic gradient descent, or some of its variants are used for like all the training in the world. Okay, it's not all the training in the world, but it's like 99%, right? So it's like all the training in the world. So it's fine. And how I look at it is that it's a wrong step in a wrong direction, right? We do not know how big a step we should take. The direction that we computed is also wrong, because we do not want to go in that direction, but it kind of does the job, right? Which is weird. But still, let's look at the picture. But to understand this picture, we actually need to include something more in the picture, because our function should be a sum of, or mean of more functions. So how to visualize this? So let's say that this is the first function. These are the contours of the first function. These are the contours of the second function. And if I average them out, I should get the contours which I have under that. Just very intuitively. It should work. So I'm again starting here. I'm going to flip a coin and say that now I'm going to choose this function and the gradient towards this function, right? So I'm going to take a step towards this minimum. Now I'm going to take this one and take a step towards this one. And again, and again, again. Oh, solved. So, anyway, it does not make sense, but it makes sense, right? In some sense. So what it means is that it does the correct step, in some fashion, right? It's one of the functions that we want to optimize, right? So if we optimize all of them once, we should do some good step in the end, right? But it's actually not that easy, and it's not that easy to prove that it works, and it requires some math again, but it's going to work. And this is the idea that stands behind most of the learning done today, that stands behind, the Google being recognized that what is a cat or what is a dog, and so on, which is the most important challenge of all. Okay, so I have one slide where I just briefly explaining that why this makes sense. Again, it's going to be slightly more mathy, but again, just get a beer. If you hate math, it's fine with me. I can totally understand that, but we should talk afterwards. So the idea is that the direction is actually correct in expectation. What does it mean is that if I just look at the expected direction, if I just chose the example randomly, it just rolls out as this mean over all the possible directions, because it's just average of all the directions. And that's actually our gradient of the big F, right? Which means that in expectation, we are going in the correct direction, which is at least some good news, right? It's better than nothing. But the variance is not vanishing. And what does it mean is that, some symbols, but what does it mean is that if we actually hit the optimum, if we actually come to the minimum, and we continue with the algorithm, we are going to jump out of the optimum. Because those small gradients do not have to be 0, just their sum has to be 0. Right? -1 and 1, okay. The sum of -1 and 1 is 0, but it still means that one is going to push in one direction and the second one is going to push in the other direction. And there's a very bad property of an algorithm. If I was so lucky and to start the optimization at the optimum, I will actually jump out of the optimum. And I will probably not return ever again because, that's just how those algorithms work, that they usually do not visit the same point twice, right? So that's very unfortunate. And one of the things that are fixing SGD is that the step size that I mentioned is decaying. What it means that it goes to 0, which means that, the step size is going to push the algorithm to converge. Because if we are going to take smaller and smaller steps, in some time, we are not going to move at all. And we are going to converge to some point. It's not going to be the optimal, but it's going to be some point. So, at least it converges. But this is actually happening, This is actually the thing behind SGD. This is actually the thing behind all those training of deep learnings and so on, right? There's nothing more to it. Okay? So, just one quick note. For the gradient descent and randomized coordinate descents that we discussed, this is actually not happening because the gradient at the optimum is 0. That's how math works, right? That's it. So, those are fixed. And I was actually requested to include one slide. This is the reason why I include this one and one more slide to show you some cool optimization methods. So the next slide is going to be about the cool optimization method called stochastic variance reduced gradient, which somebody, cool guy named I think Rai Johnson and Tong Zhang, those are two guys, not cool, developed and proposed in 2013 to actually tackle this issue with the algorithm jumping out of the optimum. So the algorithm is slightly more complicated. It contains 2 loops, not just one, that do this, but do this, then do a lot of that, and then again do the first one, right? So the outer loop is just take the current iterate, then store it as that, and compute its full gradient. That's very expensive, we already discussed that, that's n times d, right? That's the big number. But whatever, we are going to do this just once per n iterations. So it's basically, if we compute one gradient once every n iterations, that's like computing one small iteration. Just, some math again. So, and the inner loop, there is repeat k times because, whatever, but it should be n, that's fine. We are going to just sample, pick one of those functions, and we are going to do this step. Don't worry, this is going to be probably the most mathy thing that you are going to see today. And the idea is as follows. So, at the beginning of the inner loop, when w equals z, right? This minus this plus this is 0, right? So we are just taking a gradient step at the point z, which is good, right? And in the next iterations, we have like a general direction, which is like the gradient from a couple of iterations before, corrected by the current point. It's like weird, it does not make sense, but whatever. Let's just assume that it's fine. And now let's look at what's going to happen at optimum. So at optimum, if here we are optimum, z is optimum. Yeah, there's an arrow, cool. Z is optimum, then this is 0, this is 0, also the small gradients are 0, everything is 0, we are not going to move. Oh, job well done, we are not going to move out from the optimum. Okay, that's what we wanted to do. And now, okay, does this make sense beyond, we are not moving out from the optimum? So, if we look at this term, this is actually 0 in expectation. Because again, it's just the gradient of the small function. If we take the expectation over it, that's the gradient of the big function. And they are just going to cancel out. This one is just the same as in SGD. So the expectation is just the gradient. So in expectation, it's the correct direction. Good. So it's the correct direction, and we are not going to move from the optimum. That's just great. 2013, and since then, yeah, this works pretty well for large data and some of the problems. So what do you think? Is it cool? Because I do not think so.
How well does it work?
It works quite nicely. I could show you some picture which would basically just say that SGD and SVRG. You know, it's like,
Yeah, sure.
I cannot do more. In some sense, if you have, for example, a problem which is linear models, the standard one, then this is going to converge like 1 over t, and the second one is going to converge log 1 over t, so much faster. That's a mathy answer. I can again point you to some papers. But again, just put this into Google. And I really want to talk to you after. Okay?
But you said it works well for some problems.
Yes.
What kind of problems? Or what does it not work for?
It works best for strongly convex problems, which is an issue. For deep learning, it works slightly worse. There are better methods for deep learning. We'll just say so. So, you know, on the scale from nice problems to deep learning, it's somewhere here. So it's good. Yeah, in general, there is no method which works good for very well for everything, right? So one has to live with that. Okay, and that's it for big data. Do you have some questions about big data? It's a cool thing, so I had to include it, but you know, otherwise, at least one.
What about the higher order derivatives?
Yeah, that's an interesting question. So the higher order derivatives for big data are actually quite unfortunate because computing a gradient is as big as the number of dimensions. Computing the second order derivative is as big as the number of derivatives squared. It's actually a matrix. Which means that just computing one of those second order derivatives takes a lot of time, right? And you're going to do a better step afterwards, but the question is whether it's worth it. Usually it is not. So if you have a big data regime, like really like billions and so on, second order information is close to never used. For smaller problems, it's definitely the best thing to do. But for big data problems, it's not the thing to do. Good question. Okay, let's move on because yeah, definitely. Okay, so now I have just a quick intro to distributed problems, which is another kind of difficulty. So if you have that much data that you cannot fit it into a single computer, then it starts to be difficult again. So think about it this way. We have one computer, there we have a couple of functions. On the second computer we have different kind of functions, like think about, you know, some laws over all the users in Europe, over all the users in America, you know, all the users in Africa, and something in between, right? And now what we want to do is to figure out the best predictor over them all. That's it. But, you know, communicating between them is actually difficult. So usually there is a master node, which is trying to minimize over all the population, not just in different continents. And it can communicate between all of them. But the communication is very costly. It's usually way more costly than computing a single gradient or, you know, than doing even like thousands of gradient steps. Usually the computation is the bottleneck, right? So if you think about it very naively, what you can do is to do distributed gradient descent, which means that you just compute the gradient here, 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 send it here. It has the full gradient, it can do a gradient step, you know, distribute the new point here, 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 and just repeat. But you are doing one gradient computation over one communication, which is very, very costly. So that's quite bad, and the communication is the bottleneck here. The second naive approach is the so-called one-shot averaging, which means that let's just find the optimum here, let's just find the optimum here, here, just communicate the optimum, and just take the average of them and hope that it's going to be fine. Because there's not much more you can do than hope, because it's going to be bad, usually. But sometimes, it can be good. So, the accuracy of those predictions are actually quite bad. And what changes actually when you look at distributed stuff is that usually you look at time, which it takes to optimize as the number of iterations times the computation per iteration. That's a very standard thing. So if a gradient iteration takes 1 second, then I need to do a million iterations, that's a million seconds, that's okay, I should take a day off at least, you know. Probably more? Way more? How many seconds is in a day? A lot, okay. So, and the distributed convergence time is slightly different because it takes into account the communication, right? So suddenly, it's not just how much time does it take to compute the iteration, but also how much time do we spend communicating the iteration. And, you know, in the distributed gradient descent, this was small, this was big. In the one-shot averaging, in some sense, this was small and this was big, because we computed the actual optimum and just communicated once. So ideally what we would like to have is these two to be similar, because otherwise one of them is a bottleneck. If they are similar, we cannot say that, you know, the algorithm is bad because of this, right? It's bad because of both of them, or neither one of them, right? So yeah, ideally. And now I want to give you just an intuition of how such a method can be designed, and it's going to be with a picture, so it's fine. But first, let me just describe the steps. So the first is that we compute, again, as I described, the minimizers at each of the nodes, exact or close to exact. Then send the minimizing vectors back to the master node, as was done before, and then we just took the average and, you know, we were done. But this time, we are going to create new objectives for the local nodes. What does it mean is that we are actually going to say that, you know, before you try to optimize this function, now try to optimize this function instead, which is kind of shifted towards the optimums of the other ones. That's basically the idea, that you want to be closer to these ones because you know, the other ones outputted different results, so you should be close to each other. And then just distribute these local objectives back. This sounds complicated. Let's look at the picture. Okay? So let's say that these four are the optimums of our local objectives at the beginning. So Africa, America, I wanted to say US, but that sounds similar. Europe, Asia, I suppose. So now let's pick one of them and try to figure out that how to actually update the objective of this one. So these three, you know, have some sort of mean here, and we would like to move towards this mean. So how to enforce that? So if we add another objective, some sort of, you know, contoured function, and we add it to this one, then the minimum is going to be somewhere in between these two. And that's basically the idea, the main idea. So we just add this function to the one that outputted this minimum. And what it's going to do is that it's going to move the optimum from here to here. And we are going to repeat this for all the nodes. So here are the three of them, here's the optimum, and we are going to step here. And for all of them, one after the other. And these are our new objectives. And now just repeat. Compute for each one of them, just go, and so on. Does it make any sense? Okay, good. I'm glad. Super happy. At least one. Okay, if it doesn't make sense, do you have any questions about it? Or it just math, go on? No? Okay, but everybody's still here, so I suppose that it's fine. Or maybe we can blame the weather. Yeah, probably weather. So, the last part that I want to talk about is probably the most interesting, I don't know, probably not. But some of you might be interested in this, let's say so. So, complex objectives, and I do not mean complex numbers. I mean like complicated, right? So, what I mean is that most of the optimization, or some of the optimization, has some problems when it encounters complex objectives as, you know, deep learning, where the function is just complicated. There is no better word for that, right? It's just weird. So, deep learning, it has one big pro, and that is that is just super cool and it works. It's the ultimate tool for machine learning. It actually tackled many of the problems that were not solved before, image recognition and so on. With deep learning, it seems to be just easy somehow. But for a mathematician, there are two kinds of mathematicians who look at deep learning. The first type is me. It's a nightmare. I do not want to, do anything about it. And then there are the second ones who consider the ultimate challenge to figure out, to actually prove that something can be done with deep learning. Somehow we can optimize it. And the problem is, from a mathematical perspective, that it's optimizing a function without any assumption. You just have a function, and it's continuous, and that's it. You cannot assume anything more, right? And try to optimize that. Difficult. Not so easy. I do not know that if I stand here, whether the point next to me is here, or just, there, or there. That would be weird. And the other things is that we do not have real guarantees on how well the deep learning generalizes. So if we just optimize the error, how well will it work on other cats that I have not seen before? There are all these heuristics which solve it, like dropout, regularizing, and so on, but there are no real guarantees which would actually prove mathematically that yes, this is happening, this is always going to work. And I do not like this, but that's me, mathematician. So, and there are no real guarantees on convergence even, that we are actually going to converge somewhere. So we do not even know that whether we are going to converge to a good point, and whether that point is going to be good, actually. But still, and that's just great, it works, right? And while it works, we should, not really care about it, right? So, deep learning is actually super popular right now. 1/4 of all the papers submitted to NIPS this year, which is one of the largest machine learning conferences, was on deep learning. In comparison, I think that the second most popular topic has had around, 1/8, 1/10, something like that. So, yeah, there are many topics in machine learning. Deep learning was just, every time, everywhere, in every room, there was a lecture on deep learning. And what I want to do at the next part is that I want to just tell you something probably, I hope, new about deep learning by looking at some problem where it fails, where it actually does not work, and probably to learn something from it. So there's this problem of learning parities, which actually which was put online as the failures of deep learning by Ohad Shamir like a month ago. But I discussed this with Ohad like half a year ago, and he seemed to be super excited. So I was just waiting for the paper to appear and to do this talk. So the idea is to learn a function which outputs the parity of active entries in an unknown subset of coordinates of a vector, which sounds super complicated, but basically what is the idea is that you have a binary vector, you look just at some of the entries and you say that how many of them are active, and you take the parity, either even or odd number of entries. So formally, there is some sort of vector v, and our function is -1 to the power of v inner product x, which if you think about it is just v acts like a mask, so we look at just some of the entries, and we just count the numbers where v is 1 and x is 1 at the same time. So the parity of active entries, and then it's going to be either 1 when it's even, or -1 if it's going to be odd. That's it. It's a very simple function. Everybody here should be able to be a good predictor for this function. I hope so. And the idea is that to learn this function without any information on the mask. So we do not know the mask up front. We want to learn the mask as well as the parities just by observing the ones and the -1s, so the labels for the given examples. And it can be simply proven that if you take just a simple neural network with one layer and 3/2 times d units, there is such a network which is going to do this. Exactly. So that's good. And I'm going to show you an experiment which involves 10d instead of just 3/2. So let's just give it some room to, to figure it out. And still just a single layer. So what's happening is that for d equals 5, its accuracy goes to 1 quite quickly. It just learns the thing. For 10, it does nothing and then it learns it. For 30, however, there is some issue. And the question is, should we just learn for, longer period? Should we just have a deeper network as, it usually solves the issues? Or what is actually happening? And actually, one can kind of prove that it's not going to learn it at all. Which is kind of surprising. But there is actually some theory behind it, again some math, but not that much. And the idea is that the gradients are going to be completely non-informative. What I mean by that is that independent of the v's, we are going to have very similar gradients. Like very close, to each other. So the gradient information is going to be the same for all the v's, which kind of sounds like we cannot do anything because we just want to figure out what is the v, right? So if we look at all the gradients of the losses for all the v's, just as I described right now, there are going to be some points in some space, and their variance, so how far from each other they are, is going to be upper bounded by some term going down with an exponential in d. So with these 30, this is going to be a huge number, probably even larger than the machine precision, and therefore we are not going to be able to do anything. And this is actually quite difficult to understand that why this is happening, and there is a long paper on this, involving, all kind of funny stuff as Fourier transforms and so on. So I do not recommend you to read this. It was a pain. And there's actually something more general for linear functions composed with periodic functions. So think about a linear function inside a cosine. This is also not going to work. And one can prove this. Ohad again did this. And the reason is simple, because the function looks like this. So it's completely flat, except of a couple of holes. And those are the ones that we want to find. We want to actually be here. What does it mean is that you are basically wandering over a very flat region and just hoping that you are going to fall into a hole. But think about this in like million dimensions. And it's, it's quite, it's not so probable that you are going to find that hole, that you are going to hit any hole at all. And yeah, this is the idea of the non-informative gradients. So what I took from this is that even such a very easy task as learning the parities, some given subset, blah, 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 active, that kind of stuff that I talked about, is actually difficult for deep learning, and not just for deep learning, but for any kind of model, where for training we use just first order information, so we use just the slope. If we would use also the curvature, we could probably do something more, but because most of the methods today use just first order information, they are not going to work on this. Which is very weird, because nobody wants to learn such functions, right? But what if some kind of sub-problem in your big machine learning pipeline has this kind of structure? Just a small part of it. It can have issues, to learn this small part, which you do not even know that it's there, right? So, if such a simple counterexample exists, how can we be actually sure that the deep learning will succeed on our task? We cannot, but we hope, right? This can be, I'm not claiming that it is, one of the reasons why deep learning struggles on some of the problems. Any questions about this? Yes?
Do you know about any real-life examples that would translate to this kind of concept?
I have actually not thought about this, so I do not know an example right now, but that's an interesting question, yeah. But you know, like learning parity seems you know not so artificial. Let's just say so. Okay, I have one last slide actually. So yeah, I just want to do a final recap of this whole talk. So what I wanted to say in this talk is that optimization is kind of a backbone of the machine learning, right? What I mean by that is that it's completely fine not to know anything about it until it starts hurting, you know, until something's bad, right? It's completely fine to do machine learning without knowing anything about optimization. But once something goes wrong in the optimization part of machine learning, there is a possibility that you are not going to solve it unless you know something about optimization or unless you know somebody who knows about optimization, right? Most of the time, it's actually not important for a practitioner, really. Like, that's one of the points of this talk. Do not care about machine learning, right? Or about optimization. Care about machine learning. Machine learning is cool. The second thing is that optimization offers a lot of challenges, and most of them are very well suited for mathematicians. So if you are a mathematician and you want to do something more applied, but also theoretical at the same time, because there is a lot of, you know, guarantees and so on, optimization for machine learning is a very nice venue for you. And one more thing is that, you know, by analyzing failures in optimization, many new heuristics, but also like good methods were figured out, like the variance-reduced SGD, for example. Okay, there was a problem with bit variance. Somebody proposed how to tackle the variance, right? So, like, I actually tried to Google up who said this, but everybody did, right? So, you know, just put here any name, really. Like, everybody did say this. So, learning from failures is the key to success. Blah, 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 you know. Sure. But actually, many of the things which are now considered state-of-the-art for optimization for deep learning or for machine learning was actually figured out by analyzing the failures of these approaches. So I suppose that with the problem of parities, you know, somebody is going to come up with a fix very soon. The problem with generalization, dropout, you know, so on. There were things which were invented just because of this. Yeah, and if you have any questions, then, you know, from my side, that's it. And I think that we can use Slido for questions. Is that so?
Yeah, hopefully. Okay, so nothing came so far. But maybe all the questions have been already asked.
That's possible. I tried to, you know, encourage them. But...
Anything from the audience?
I have one remark on my messenger, but I do not want to answer it right now.
There is one.
Yeah?
So I would like to ask you, how do you define deep learning, and why do you think that deep learning is failing in that flat region, in the partition, not partition, in the parity problem?
Yeah?
And other algorithms would not fail?
I think that other algorithms would fail as well. That's the point, right? but the point is that, you know, deep learning seems to be the universal hammer in some sense, that it can actually, with enough layers, with enough units and so on, you can actually solve nearly any problem, right? But just as a simple problem as learning parity seems to fail, right? So something is wrong, and probably we should just, you know, change something very slightly, and deep learning can work again, right? So, you know, the bottom line is not that deep learning fails and therefore some other algorithm is good. It's like we are still failing in learning these type of problems, so we should do something about it. So let me put this straight. I have no idea. I think that the probability is reasonably small. That's why I said that you do not need to know about optimization. This talk was, one way of putting that, okay, I actually do not need to know anything about optimization. But most of the good machine learning practitioners that I know actually know a lot about optimization because it drives their intuition, and that's it. They just know the basics, or sometimes even more advanced stuff, and therefore they can actually design, their methods to do better and so on. So it's not important, but it can be important. It's like, how important is juggling? Sometimes, maybe once per life you will be asked to juggle, or otherwise they will shoot you. You do not know, right? So probability, I think that the probability should be conditioned, right? And what company, which post are you working on, and so on. So yeah, somebody can do this research, but I really do not know. But as I said, it's low. It's really low. What's that word? So, okay, I will just assume that I know what it means. So I suppose that what it means is that matrix vector products, that you can actually do Hessian optimization just by using matrix vector products instead of actually computing exact Hessians. That is true, but there are still issues with it because you kind of need to estimate that. If you directly mean LBFGS, it does not work for really big data, if that's the answer. If not, whoever said that, I will be glad to take it offline. I do not think that most of the people would be interested in this in detail, but it's definitely a very good question. So after we finish the talk, just stop by me and we'll discuss. What do you do exactly on your PhD thesis? Oh, 3. Are you guys really interested in this? I just can't believe you. So, that's a good question. So, I told you about all these methods and how they randomly choose a coordinate, they randomly choose an example. And usually what's done is that it's just uniform random, that you just pick everything with the same probability. But we actually managed to show that in some cases, if you use non-uniform probabilities, you can do way better. So I was kinda, randomly exploring this random thing. And I managed to come up with some, algorithms which work better. And one of them is actually inside TensorFlow core now. Just bragging. So yeah, I'm working on this part, which I find is quite interesting because nobody's working on it, which means that it's not interesting. Which kind of, answers my, counters my argument about it being interesting. But yeah, it's fun. So, more or less this. Wrong step, wrong direction, or both of them, yeah. So, the answer is basically simple, so just use the fit function. So, the fit function just calls the best that it's for that problem, usually. Or if you just briefly read in the documentation of the fit function, you will figure out that, okay, you should use this function if you have this kind of problem, or this optimizer if you have this kind of problem. Everything is implemented. You do not have to do nearly anything. And as I said, there is no just general method which works well for everything. there are methods which work good for this, methods which work good for that, you know. So if you really have some problem which is not inside fit, which cannot be solved by fit, and it's a machine learning problem, then it's probably getting out from machine learning slowly. It can be more of a financial problem, more of a modeling problem, and so on. You know, there's no general answer to this. Really, one has to pick the problem first. If you would ask, like, what's the best algorithm for this problem, I can probably tell you. But in generally, it depends. Okay, I think that, like, again, subject to opinion, that Kaggle is an ecosystem of its own, right? So, what I heard from a couple of people who competed in, who organized some competitions in the Kaggle, said that the algorithms which usually win those competitions are not really usable in practice because they are so well fitted to the problem that it's just not going to work then. So depends. This very much depends. I do not think that I am the one who should answer this question because yeah, it's not really optimization related, but yeah, deep learning is hammer. But I think that there are people in the audience who could answer this question better. Who thinks that has a very good answer on this? Oh no. Yeah, sorry. How does the research in optimization look like? Are you just, you know, waving with hands? This is good, I like this. So basically how it looks like is that you go to see your supervisor and he says that I think that this could work. And you just need to figure out that how, right? So this is how research usually looks like. From the point of view of my supervisor, his research, how it looks like, is that he reads a bunch of papers, he attends a lot of lectures, and he realizes that, oh, this can be applied to this to solve this, right? So you kind of know that what kind of problems there are still in optimization, what kind of methods there are to tackle those problems. And if you have a very good intuition, you can figure out that which problem to apply to what, such that it's going to be novel, and at the same time it's going to solve the problems which appear, right? So, yeah, and then just come up with this idea and call one of your students and just tell him about it, and he's going to be super excited to do some work in research, and you know that you just have to wait for the answer, whether it can be done or not. So I think that research in most of the fields is quite similar, like mathematical fields, which means that, you know, there is some method, there is some problem, these were not combined before, that's it, right? I actually attended one lecture at NIPS, and it had this very insightful slide where they said that, okay, we have this you know, bandit learning, stochastic gradient, descent, we have this Monte Carlo learning and so on. And right now, we published a paper called Learning to Learn by Gradient Descent by Gradient Descent. And he said that, okay, and now all of you, there are like 81 combinations how you can put all those learnings together. So you do learning to learn by Monte Carlo by bandit learning, right? Go, right? So a lot of research is about combining ideas that have been already developed, and really just sometimes there is an idea which was not developed before and a completely novel approach. And those are mostly done by very smart people who are doing that research for many years. So yeah, I hope that this answers your question. What do you plan to do after finishing the PhD? Yeah, I'm going to work in some company. It's probably I'm currently a data scientist at Operam, so I'm probably going to stay there because, you know. And what happened? And yeah, so just the bottom line is I won't stay in academia, definitely. Nobody's going to, you know, put me there because it's so bad. Sorry, again, subjective opinions. Don't take any of this personally.
Yeah, okay. So both hands.
Right now, definitely. Okay, thanks.
So thanks, Dominik, for a great presentation. I hope you all like it. And I also forgot to ask my usual question at the beginning. Who is here for the first time at Machine Learning Meetup? Is there anyone like that? Did you like it and will you come another time? I hope so. Okay, so thanks a lot again. Please enjoy small refreshments and we will switch to football here for the football fans and we can continue talking about math and stuff. Thanks, have a good evening.